Most people live their lives never thinking about the power beneath their feet. It's not until a geyser issues forth, or lava breaks the surface, that we realize we live on a ball of molten rock flying through space at thousands of miles an hour. Encounters with the subterranean shake the image that we live peaceful or sedentary lives in an ordinary place. These incredibly destructive, powerful forces are also the lifeblood of our planet. Earth's geodynamo not only powers these mountains of fire, but allows us to live in a hospitable place, one with an atmosphere and a protective magnetic shield against the intense radiation streaming from our nearest star. It allows us to access the metals and minerals that enable modern society. And in human history, the power of volcanoes is etched into almost every oral and written tradition that we know of. Hawaiian, Indonesian, Indigenous American, European, we have always lived in fear and awe of the power of volcanoes. Today, we're talking about the future of volcanology. All right, welcome to Giant Leap. I'm Taylor Wilson.
And I'm Joey Lovato.
And we're talking about volcanoes this week, Joey.
Hot mountains.
Hot. That's one way to think about them, yeah.
That's how I think about them. I have the closest to a volcano I've ever been. I've been to Hawaii, but I've never seen lava in real life.
You've never seen like a lava lake?
No, have you?
I've seen quite a few volcanoes.
They kind of freak me out a little bit.
I really like volcanoes, and I have my special interest in them, the geology of them, the microbiology of them.
Sure.
But they're just this, unique insight into the way the world works in a way that most people, I think, don't think about. You live your everyday life and you don't think about the immense temperatures and pressures beneath your feet until, you hike to a geyser or you hear about a volcano erupting on the news, and then you're like, wow, there's a lot of energy beneath our feet.
Beneath us. Yeah, I mean, we see that here in northern Nevada where we live we have hot springs and a lot of geothermal activity.
Yeah, and a lot of volcanism in that part of the world.
But yeah, it's not something that I interact with on a daily basis. I'm not interacting with volcanoes on a daily basis.
But that geodynamo, it's going beneath our feet.
Well, and so that's one thing is, geodynamo, that's the earth. That's like the engine of the earth.
Yeah, I mean, think of it, dynamo power, geo, earth. It's the power of the earth, and it's really important, that fuel source that fuels everything from volcanoes to, the magnetic field that protects you and me and our atmosphere from the radiation of outer space.
That's all from the heat under us that came from where exactly? Like the formation of the universe, basically?
You can think of it as kind of these 50-50, these buckets. One part is primordial heat, and primordial heat is literally leftover heat from the formation of our planet.
Okay.
So you can imagine...
Just still trapped inside. It's slowly dissipating.
Yeah, I mean, think 4.5 billion years ago, the Earth was very hot. It was formed by the collision of all these kind of rocks that were floating out into space, and that was an incredibly energetic process. And even though you follow these laws of thermodynamics and that energy kind of radiates out into space, 4.5 billion years later, we still have a lot of that
takes
heat
a while
left. Yeah. So that's one bucket, and then the other bucket is my favorite part, which is radioactive decay. Those radioactive elements that are still remnants of an early supernova.
They're all a little warm, right?
Yeah, uranium, thorium, potassium. You're right now surrounded by a lot of those radioactive rocks, and any individual one of them is not particularly radioactive or particularly hot, but you can imagine a whole Earth's worth of rocks that have those elements in them.
A little warmer.
That decay, that radioactive decay really heats things up.
Yeah.
And those are the power sources of this geodynamo, which powers volcanoes and hot springs and geysers, and, again, our magnetic field, which is the only reason really that we could be here to have this conversation.
I love the magnetic field. People love volcanoes. We talked to scientist Clive Oppenheimer, not related to the Oppenheimer that created the nuclear bomb.
Yeah, but a fascinating scientist nonetheless. Clive is a volcanologist at the University of Cambridge in England, and really one of the world's foremost leading experts on all things volcanology. So it'll be exciting to dive into a conversation with him about this.
Yeah, worked on a documentary called Into the Inferno with Werner Herzog, right?
Yeah, which I can't recommend enough. enough.
Yeah.
I mean, it is a fascinating look at the cultural context of volcanoes, and Clive is a very prominent part of that documentary. But anyway, yeah, let's dive into it. So, Clive, I guess to start here, what is the future of volcanology look like?
I think one thing that's humbling when you look at the history of the science is that 250 years ago, people were asking the same questions that we're asking now. You know, what is it that makes volcanoes work? Why do they erupt when they do? Why do they stop erupting? So I think the future, realistically, is going to be still trying to tackle those really difficult questions. But I think, you know, there are a lot of technologies that are increasingly in use. I came into this using satellites to monitor volcanoes from space. That's something that only ever gets more and more sophisticated, the capabilities of observing volcanoes around the planet. Also, the use of drones. I've got colleagues who fly drones with sensors into plumes with, again, increasingly sophisticated packages of sensors and samplers to make measurements where it'd be very difficult or dangerous to go. In the lab, we can use very high energy beams. For example, at synchrotron radiation sources, we use those to analyze the most microscopically small bits of a rock erupted from a volcano to figure out how deep down in the crust did it form. So there's a lot of tech. Something else I reflected on, I think also the future of volcanology is women. It's a science, I would say in my career, the PhD students that I've been the advisor for, probably 50-50 male, female, but it's certainly been a transition over my career, seeing increasingly women involved in volcanology, going out in the field, working in the lab, modeling.
I know that with volcanoes, it's kind of a regional thing, right? We have the Ring of Fire, and they're all often found around the equator. Is that where the minerals exist that kind of lend themselves to volcano, or is it more of like that? Is it more of a crust situation? I guess I'm curious, like why they're forming in these areas, and is there like a Goldilocks amount of materials or types of materials that tend to lead to volcano creation?
I find a lot of young people coming out of high school, middle school, high school. They read that if you go down into the earth, it's all molten magma just waiting to bubble up, and that's not the case. I mean, the places where we find volcanoes are very specific places along these tectonic plate boundaries, as you say, around the edge of the Pacific. Also in the middle of plates like Hawaii, which is bang in the middle of the Pacific Ocean plate. And what's going on there is that the rock of the Earth's mantle, its main layer, has reached conditions where the solid rock starts to melt. Some of the minerals in it melt, and that liquid then migrates upwards and starts to accumulate and becomes a magma. And because it's more buoyant than the surrounding rocks, it can rise up through the crust. And ultimately, some of that might erupt. And so most of the volcanoes we see on Earth are connected with the plate tectonic boundaries. And this tectonics is really about the Earth losing its heat. How does it lose its heat from leftover from its formation 4.5 billion years ago, and from radioactive isotopes within the Earth? How does it lose that heat into space? Tectonics is really the main way that it does that, and the volcanoes are connected with it.
I don't think of radioactive materials and volcanoes as really having much to do with each other at all, but I also don't know very much about volcanoes. So are those things related?
Let's go back to why is the Earth hot? Okay, I mean, volcanoes are demonstrably erupting stuff that's down there that can be 1,000 degrees Celsius. Or more. So it's hot down there. That heat, some of it is what we call primordial heat. And that's left over from the Earth's early formation when it was bombarded by lots of asteroids, a lot of kinetic energy turning into thermal energy. There were some short-lived isotopes that provided a lot of heat in the very early Earth. And today there is still heat production from isotopes of uranium, thorium, and potassium. And they're producing heat, they're generating heat. If we look at globally how much heat production is going on in the Earth, it's about half of what the Earth, the heat that it's losing into space. So the Earth is cooling down very, very slowly. The kind of main thing that's going on in the Earth, in the mantle, is this convection process. So even though it's in the solid state, there are currents of rock that are taking heat from the deep interior of the Earth, from the core up to the surface. And as those currents of rock, think a glacier is solid, but it flows. Okay, so rock that's solid can flow at high temperatures. As that hot rock comes up approaches the surface, the pressure on it is reduced, and a little bit of it starts to melt. And that happens in these specific places, like around the edge of the Pacific. And that's why we find it quite localized, this melting process that then leads to volcanoes.
You kind of hit on an interesting point there, which is, between radioactive decay heat and primordial heat. It seems like we're kind of in this interesting, at least in the geological history of this planet, this interesting time period. And that makes me think about Mars, which of course we used to have massive volcanoes and lots of volcanism. I think about, planets like Venus that might still have some active volcanism. What is the future of the geological history of this planet as the radioactive decay heat becomes less, as we lose that primordial heat? Will Earth start to kind of shut down? Will volcanism start to wane? Is that the future of this planet?
I would think that that's inevitable unless there's some other source of heat. Maybe another big impact of some moon-sized object will impart a bit more heat and stir things up again. But there are people who work on plate reconstructions back through time, but then also projecting them forward into the future. Where will the continents move to, given their present trajectories? But yeah, it's a big pot of soup, and it's cooling down because the burner's being turned down on it.
I grew up in the southern United States, and certainly we don't have a lot of recent geological activity in that part of the United States. And then, as a teenager, I moved out west and to the western United States, where we are adjacent to, this plate boundary. And there's lots of, volcanism and tectonic activity. We've got, the Cascade Mountains. And I loved that. That for me was an amazing experience to move to this place where there were all these active geological processes, and I could go look at hot springs and fumaroles and volcanoes and all of these things. And for me, I think a lot of people think that volcanoes are a very destructive thing, right? They think about Pompeii and these disastrous events, at least in human history. But I have developed this appreciation for the I guess you could call constructive aspects of volcanoes, the emplacement of minerals, gold and silver and diamonds, and the soup of material that comes out of these volcanic vents that can spur on the evolution of life and all of these things. Do you kind of have that sense of volcanoes as being a constructive versus a destructive thing?
Can't live with them, can't live without them. One of the things I've wondered about is, could life exist on a planet without volcanoes? And given their role in generating a primary atmosphere and the way that they continue to modify atmospheric composition, along with plate tectonics, I think it's probably not a coincidence that we're on a planet that's got both of those things going on. I'm not the first, I think, to think of the constructive destructive. Actually, one of my heroes is this guy, William Hamilton, who was a British envoy in Naples in the second half of the 18th century, often touted as one of the first serious volcano observers. He was fascinated by Vesuvius, and he made this fabulous treatise on volcanoes, focused on the volcanoes of southern Italy, with beautiful sketches, colored sketches, and a bit of text. And actually, one of the things he wrote that motivated him to do this was that he wanted to show volcanoes in a constructive light because they're so often portrayed in a destructive light. And of course, he's right there where Pompeii is, and it's when they're also pulling all the Roman statues out of the ground. So volcanoes had that kind of bad press from early days. And of course, we focus on the catastrophe in the news. The volcano is not in the news unless it's shut down air traffic, or unless people have been evacuated, or people have been caught in pyroclastic flows. Then it's in the news. There are very long periods of time between these catastrophes when we live with volcanoes and benefit from their resources. And I think that's been going on throughout time, as long as we've been on the planet.
Yeah, how big of a danger do volcanoes, pose to humans compared to other natural disasters like earthquakes or fire or flooding?
Some time ago, actually, there was a lot of interest, I think, partly from these movies, Deep Impact and of an asteroid impact. And we looked at, well, okay, volcanoes, very large eruptions are also extremely energetic events. And but then you've also got to look at what's the frequency of these events of different sizes. How frequent is the bolide that could change global environment? How often does that kind of event recur, compared with how often does what we call a super eruption occur, like the one 74,000 years ago in Sumatra? And at the very large end of the scale, I mean, actually, the volcanoes are potentially more energetic, and they can change the global climate from the dust that goes up into the atmosphere. Colleagues have looked at whether they pose an existential threat. As a species, we've lived through some extremely large eruptions, including the event 74,000 years ago. We're still here. I don't think they're at that level, but certainly they have high potential to be extremely disruptive, and of course, it's going to depend on the nature of the eruption and its location, which part of the world, and there can be all kinds of ramifications: the humanitarian side of things, economic, supply chains, transportation infrastructure, communications, all of that can be interrupted by volcanic eruptions.
Yeah, I think most people probably, when they think of volcanic eruptions, they think of the local effects, right? Whether that's ash falls or lava flows, or the impacts to air travel in Iceland when there's a eruption. But I think back to things like Tambora, 1815, these massive, absolutely massive eruptions that caused global scale impacts. I mean, is that something that you think there's at least some probability we see in our lifetime of these kind of global type disruptions to climate or agriculture, from a volcanic eruption?
Yes, certainly. More likely in your lifetime than mine, just I'm a bit older. But yeah, absolutely. And the last, I guess, the event that really showed us how volcanoes change climate was in 1991, the eruption of Pinatubo in the Philippines. And that's about 1/10 of the scale of the Tambora eruption in terms of magnitude, the amount of pumice that's produced. So a big event that's about has a return interval of around a century. That size of event. A Tambora event maybe somewhere several centuries return, 500-year return, something like that. So there is probabilistically these things will recur. I mean, it'd be daft to say, oh, actually all the volcanoes of the world switched off. They're behaving differently. There will be future very large eruptions, and I think that is part of our motivation for trying to understand them. But one of the lessons of the last decades, Pinatubo is a good example. That was not recognized as an active volcano or potentially active volcano. It was off the scientific radar. If you'd looked at the volcanoes of the world big catalog back in 1990, you wouldn't have found Pinatubo. So it hadn't erupted in living memory. It had been subject to a little bit of geothermal exploration, didn't look very promising. and then it starts coming to life. And the rationale to this is that the largest eruptions happen on volcanoes that aren't leaky. Okay, the magma that accumulates in the crust isn't dribbling out every 5 years. It's accumulating and storing and building a bigger reservoir that, if that ruptures, that can source a much bigger episode. So these really big eruptions, I would think quite possible. If I do live to see another big eruption, I might never have heard of it before, because it'll be one that's off the scientific radar.
Is that something that we're getting better at predicting? Is that part of like what your research is doing? Is like, hey, how do we find these potentially these volcanoes that aren't on our radar right now that maybe should be?
One of the promising techniques for this is using spaceborne radar, satellite radar, and particularly a technique called radar interferometry. So with these radar satellites, we can make images, we can see through clouds, we can see buildings or damage, all sorts of things you can do with them. One of the very clever things you can do is the sensors. They measure the phase of the return pulse of the microwave energy. And if the ground has shifted between successive images, and if you know the geometries of the satellite orbit, you can actually measure very, very subtle uplift or movements of the ground. And the advantage of this, of course, is you don't need to stick a GPS antenna on a volcano. You can do it with satellites that are orbiting the Earth regularly. And that gives some scope for a global monitoring tool. And many volcanoes prior to eruption, it's not going to come up overnight. It's got to push the rocks that are in the way out of the way. That's going to cause some uplift, and that can be detected. So I think that's one of the ways that we can hope to keep track of some of these unknown volcanoes.
Yeah, that's an incredible technique. Do you know about what the sensitivity is from orbit, with these remote sensing techniques, how much of an uplift we can detect?
Certainly below a centimeter, a few millimeters, but it's also, one of the issues with the technique is that you need other things not to be changing. If vegetation is growing,
Sure.
then this is problematic. So it's a great tool in the desert of the central Andes. It's a great tool in some poorly vegetated areas. But if you go to Indonesian volcanoes with a lot of vegetation that's growing all the time seasonally, then it's much harder to see what's going on at the ground surface.
And what about seismicity? I mean, do we have a good network of kind of earthquake monitoring now? Are we able to kind of use that to better predict what might erupt next?
Yeah, certainly. So geodesy, measuring the shape of the ground, that's very important. Do it from ground, GPS, from space. Seismicity, measuring earthquakes, that's also very important. But it's difficult to do it in a global way. Yes, you can do global seismology, but that's picking up very, very big earthquakes. And the kinds of earthquakes that might presage an eruption might be very, very low magnitude, magnitude 1, magnitude 2. And that means you need a local network. Okay, so now if you want to monitor the volcano, you need to have the resource to install and maintain a seismic network there. And that's why it works great in Iceland. The things going on there are an hour's drive from the capital. It's bristling with seismometers. They can see the magma coming up. They can even see, so the epicenter is the latitude and longitude of an earthquake. The hypercenter is also its depth. And you can sometimes see the depths of the earthquakes getting shallower, indicating that magma is rising. So yeah, it's super important to do seismology, but you need a local network. And then the third thing we do is measure gas emissions. That's the other thing we do.
In those networks of seismometers and gas sensors, are those usually kind of locally ran, like national projects, or are there kind of international collaborations that will go to hotspots or areas of concern and put in sensors?
Yes, both. There will be, if you go in the States, US Geological Survey operates a number of volcano observatories: Hawaiian, Cascades Volcano Observatory, Alaskan, Yellowstone. And they will have a lot of local monitoring assets. Maybe things start kicking off on Kilauea on Big Island. Okay, they'll then bring in extra resources from the mainland to have a denser monitoring network. And then at an international level, certainly there can be a lot of support. For example, there's an eruption in Indonesia. Things start escalating there. Maybe even some of the instruments are destroyed in initial explosions from the eruption. And now they're looking at this volcano without, looking at it blind. Their sensors have been taken out. And then there are international corporations where satellite data will be made available in near real time to enable ongoing monitoring. So there is quite a lot of international cooperation, and certainly once an ash cloud is in the atmosphere, that can travel many thousands of kilometers. So this is now an international thing, and there's an international network that uses satellite remote sensing, ground-based observations, and models to forecast the trajectories of ash clouds.
And how dangerous are like the effects of a volcano outside of just like, you're like, there's the lava and the initial explosion, but from what I understand, like those ash clouds can really be the scarier effect, right?
Yeah, so I would say probably if you look at the data we have on fatalities from volcanic eruptions, let's say over the last century, they're mostly gravitational flows of one sort of another. Generally not lava flows, but rather what we call pyroclastic flows. So this is like hurricanes of ash and rock and hot gases that aren't going up into the atmosphere. They're actually behaving like a gravity current and flowing down the sides of the volcano. They might happen with an explosive eruption. There's a lot of ash and rock that blasts up into the atmosphere. Maybe that heats up enough air that it becomes buoyant and the cloud rises up into the stratosphere. Maybe it doesn't. Maybe it runs out of steam. Bad metaphor. And fountains back to the cone of the volcano, and then you get these pyroclastic flows, mud flows. These have claimed the most lives in the last century or two. What we also need to factor in is actually food security. And that can be on a local level. So going back to Tambora, there are probably around 100,000 fatalities in eastern Indonesia, on the island Sumbawa, on neighboring islands. Maybe a tenth of that was direct fatalities during the eruption. The remainder was from famine and disease because the crops were destroyed, buried under ash, water was contaminated. And then the other thing to consider is how these very large eruptions put a lot of sulfur gas into the stratosphere, how they can affect the global climate. And that's why Tambora is linked to the year without a summer in 1816, because of this sulfurous dust that can envelop the Earth high up in the atmosphere, in the stratosphere, and reflecting a bit of sunlight back into space. So there's a net cooling effect at the Earth's surface. It can result in shorter growing seasons, lower summertime temperatures, and this can impact food security, and particularly the effects from these large sulfur-rich eruptions are felt in the continental regions of the Northern Hemisphere, so North America and Eurasia. And so that's something we're very interested in, trying to understand it from a historical perspective, but also I have colleagues thinking into the future. Okay, what about the next Tambora and its implications for global food security?
You have a quote somewhere, you were talking about how volcanoes are, more of friends than we think of, and talking about long time scales. How did volcanoes kind of interplay with the start of life here on Earth, right? Things gathering around volcanic vents. We see such interesting biology happening around these vents at the bottom of the ocean. And
there are a number of things. One is these hydrothermal vents on the deep sea floor that were discovered in the 1970s in the Mid-Atlantic Ridge, where you have in complete darkness extraordinary communities of organisms of these incredible tube worms, all feeding off each other, but at the base of that is chemosynthesis, not photosynthesis. So there are bacteria that metabolize on sulfur. They can oxidize it or reduce it. That's one possibility. Another interesting one, actually, in the 50s, this Stanley Miller did these spark tube experiments with discharging very high voltage between some electrodes in an evacuated vessel with different gases. And when he put reduced gases like carbon monoxide, hydrogen sulfide, hydrogen into these vessels, he would make extraordinarily complex organic molecules. One of the places that happens is in volcanic eruption clouds. You've probably seen many images where these ash clouds are rising into the atmosphere and there's lightning playing in them. Well, you've got right there the spark tube experiment. Maybe that is also a way that organic molecules are produced. But I think even the idea of Darwin's idea of a hot pool somewhere, and there are carbonaceous meteorites that are absolutely full of very amino acids, all the sort of precursors you need for life are in meteorites, but you need to get them into an environment where they can cook a little bit. And that could again be a volcanic environment with water and heat, where you can start to get folding of some of these things to start to make proteins. So that's why I come back to this question: could life exist on a planet without volcanoes? And I'll stick my neck out and say no.
Do you have a favorite field site, whether it's scientifically or culturally? Is there one that stands out as your kind of favorite location to go and do research at?
Sure, that's an easy question. I worked with the U.S. Antarctic program on Mount Erebus in Antarctica. I went there for 13 field seasons, and that was the time of my life going down to that volcano. It's on Ross Island. So we go to New Zealand, we fly south, reach McMurdo Station, biggest scientific base in Antarctica, and Erebus is pretty close to the station. So very good logistics. And we would spend, this would be in the austral summer. So typically, actually, we get there around Thanksgiving and hang out until Christmas, come back down. Spent about a month in the field camp on the volcano. And why Erebus? I mean, scientifically, it was very rewarding. It has a perpetual lava lake. So you go up to the crater, peer in, and about 300 meters down is this lava lake. I mean, it's minus 30 Celsius, behind you. So, but you're not close enough to kind of feel the toasty warmth of this thing. But we saw some very extraordinary phenomena at this volcano. So I loved that. But I just love it was just a sensational place to live. We're in tents. It's 24-hour daylight. We're at altitude. The air is thin. It is cold. The weather can be severe. And there'd be maybe 10 of us. So we were a little community, living together, working together, fixing things, holding up when there's a blizzard, and entertaining ourselves in the field camp. So that was a sort of wonderful element to it. And in addition, just the historical side, Ross Island was where Shackleton and Scott based their expeditions to reach the South Pole and the magnetic South Pole. And so their huts are there. You see this heritage, and they're members of those teams. They were the first to climb Erebus. They were the first to make maps of it, to collect rocks and study them, and so you feel part of that legacy. It's only a little over 100 years ago that they were setting foot at the summit. 1908, it was first climbed, and there was one field season when I located a campsite that had been used by a team from Captain Scott's last expedition. And there was a little half circle of rocks where they'd held the tent down with. And a little way downwind, there was some broken glass and some remains of food, pemmican and bits of bread that they'd left when they climbed down again. And that's all the wind had blown it had snagged in the rocks. And that finding that was an incredible thrill. And again, that sort of connection with, I guess, the history of science and exploration. You're plugged into it quite viscerally on Erebus. So that's my favorite. I go there tomorrow if I can.
Yeah, completely understandable. I mean, it feels like such a, I don't know, for someone that is fascinated by planetary science and astrobiology, I feel like Mount Erebus and Antarctica, it to me kind of seems like what it would feel like to be on Mars and, you know, stand there and witness, you know, Olympus Mons or something, you know, just the starkness, the extremeness of the conditions and everything. It is on Earth, but I'm sure, you know, it feels in some ways like it's another planet.
It was kind of the conversation that originated the idea for this topic, and it's also my girlfriend's greatest fear, which is the Yellowstone supervolcano, the caldera. You know, how worried? That was the question: was how worried should we be about Yellowstone? Is that something people should be staying up at night about thinking about?
I know the guy who used to be director of the Yellowstone Volcano Observatory, and you know, I discussed with him a bit about the sort of hazards, and also, you know, there are people who will look at the data which are published online by the US Geological Survey, and then they will say there's an imminent eruption. You know, I'm calling for an evacuation within a 100-mile radius. So he's dealing with that kind of thing. But there's also a very nice report on the hazards of Yellowstone. And the thing about Yellowstone and all volcanoes is we have something called a frequency magnitude curve. Okay, so small events are very frequent compared with large events that are very rare. So the kind of thing that the super eruption scenario at Yellowstone is an extremely remote event. And there's a very nice hazards report by USGS on Yellowstone, and they go through the lesser scale of things. These are more likely to happen. These are the kinds of hazards they would pose were they to recur. And then they get to the super eruption. Okay, there have been three of these very large events in the last couple of million years. And they conclude that really the probability is so remote that it would be meaningless to try and put some kind of risk calculus on it. It's a bit like, this isn't what they say, but I think it's a bit like, you know, the probability is trending to zero, the impact is trending to infinity, and you multiply infinity by zero. It's not easy really to grasp these things. So that's a long-winded answer, but I think what is worthwhile is actually looking globally. Okay, we will get another super eruption in the future. Could be centuries, could be millennia, could be tens of millennia in the future, but we don't know currently. But that's why I think it's sensible to at least think about what are the risk implications regionally, globally, in terms of food security. We can improve global food security resilience. You know, there are things that we can do. We're not going to switch the volcano off, I don't think. But there are things that we can always do to prepare for these very large, very, very rare events.
Mm-hmm. When we have
sleep soundly would be my
that's
don't worry about Yellowstone.
Or do you feel like we're in a time now where we have sufficient early warning on most eruptions, or are there still technologies that need to be developed and systems that need to be implemented to have a better kind of early warning system for eruptions?
We use the term unrest. When a volcano becomes restless, it's rumbling, maybe there's some earthquakes, some new gas vents have opened up, maybe there's a bit of uplift. We call that unrest. Okay, globally, maybe 10% of the time that might culminate in eruption. The other 90%, the thing goes back to sleep. Do you evacuate 500,000 people on that basis, that's the where things get very, very tricky. So I think we have the tools to detect unrest, seismometers and GPS and spaceborne instruments, gas sensing. I think what we need is to figure out more finer discrimination of, okay, we see this thing, and this has been happening recently in Campi Flegrei near Naples. So the other side of Naples from Vesuvius, there's this big caldera system, and there's been a lot of seismicity, there's been ground deformation, and it's been quite alarming for the residents. This kind of activity happens on volcanoes, and they go back to sleep. So it's that how do we what extra can we do to read signs that this is one that is actually, it's going to go all the way. And then for me, I think, maybe even more important than that is the gap between science and policy and action. Okay, you can have the best surveillance in the world, the best forecasting, if you haven't engaged with a community that's threatened by the volcano, that science is useless. So there has to be also that contract between science and society to make the most of the scientific capabilities. And we can think of situations where tsunami can be detected. Okay, if the tsunami warning system hasn't been maintained, the sirens don't work anymore, all that science was for nothing, all that engineering was for nothing. So it's about keeping focused on monitoring and then also on that engagement with civil society.
Yeah, it's almost like we have the technologies, it's just refining those senses and the systems around those systems that, will need to be refined, and how we communicate risk and how we, engage with those communities. I'm sure not a trivial challenge that volcanologists face when they go into these communities, if they, come from somewhere else, to say, hey, this is what we know, this is what we don't know, and try to get those communities to, be engaged in that process, I'm sure is a huge challenge.
I read quite recently an interesting study after an eruption of Soufrière and St. Vincent in the Caribbean in 2022. And they actually looked at the communication. That this had been tracked with the various monitoring equipment. There'd been quite strong efforts to reach the community. But the people who lived near the volcano were the ones who had the least access to the internet or smartphones. So the risk messaging was least effective with the parts of the community that needed it most. And then you've got all these different ways that people are gathering information through social media, through official channels, from the radio, and so on, and sometimes with conflicting messages. So understanding volcanoes is a difficult problem. Understanding people is also not straightforward.
Well, and people have always worshipped volcanoes in the past and stuff, right? And kind of the mythical air around volcanoes. It's influenced society a lot. When you think about all the Greek gods and the Roman gods, even, and then talking about Southeast Asia and everything. Is that part of this discussion too? Is the modern anthropological effects and of volcanoes, how people worship them and think about them?
Yeah, I think that's absolutely fascinating. You can go around the world, and I think pretty much every volcano will have some local lore, stories, oral traditions, mythologies. You go to Big Island of Hawaii, it's absolutely rich with stories. Some of which, incidentally, are telling us about large eruptions of the past. This is preserved in some of these oral traditions. You can also go to Italy, Stromboli. What happens when the lava is coming down? There will be a procession, perhaps with a statue of Christ to stem the flow of lava. So we see these kinds of reactions and these stories and imaginings and meanings of volcanoes around the world. And I think that not only is it fascinating anthropologically, but it's also relevant to risk management, because you said, okay, if I turn up in Naples and say, look, I've got this incredible satellite thing and the volcano is going to blow next Tuesday, hurry up, get the laundry off the line. And I mean, it won't cut through. It's very, in Indonesia, they call it socializing. The volcano observatory staff, they go out into the community. They talk about, this is what a pyroclastic flow is. Here's a video of it. If we get to the red alert, these are the kinds of things that you should think about doing or not doing. So that if you don't understand the community that's threatened and communicate effectively with them, then the risk management is also likely to be ineffective.
In your career in volcanology, has there been a moment or multiple moments that have really surprised you when you've learned something or discovered something that really was surprising in a way?
A standout moment would have to be take us back to Erebus in Antarctica. And one of the things that's been my main technique is spectroscopy, measuring gas emissions from volcanoes. So we have an instrument, has a telescope. You pointed it, in this case, at the lava lake, and I'm measuring the infrared light radiating from that hot lava lake. I'm recording it, but certain wavelengths of that light are absorbed by the molecules in the atmosphere. And a lot of those molecules are volcanic gases that have just come out of the Earth's interior. Carbon dioxide, sulfur dioxide, hydrogen chloride, carbon monoxide, and a bunch of others. So I'm up there at the edge of the crater. This thing's on a tripod. It's minus 30 Celsius. The wind is howling. I'm trying to operate this thing with a laptop and everything's not working. I get it set up. I leave it. It collects data until the battery runs out or the liquid nitrogen cooling the detector runs out. I get hours and hours of data. When I start looking at those data and processing them, I found this 10-minute cycle in the gas composition. It became more carbon dioxide rich and then more water rich, more carbon, like this, 10 minutes. And I was so surprised that I thought I'd done something wrong. And I pulled everything apart. How could I have got this as an artifact? And I couldn't find anything wrong. And then another thing we did, we had an infrared imager looking at the lake. And from these thermal images, I could actually work out how fast the surface of the lava lake was moving. And sure enough, it sped up and slowed down with this 10-minute cycle. There's two independent things. It couldn't be an artifact. And people have been working there for 20, 30 years, had never seen this periodicity, this breathing of the volcano. And so super puzzling. We then built a radar, and we could measure the height of the lava. It was going up and down a meter or two every 10 minutes. So this thing is breathing. Wow. For me, a really fascinating bit of phenomenon. If it has a cycle, why? Why does it have a cycle? Yeah. And why is it 10 minutes? Why isn't it a half hour or 5-minute cycle? And if I can't answer those questions, there's something very basic about that volcano I don't understand, and how the magma rises to the surface, how the gas escapes from it. So, I mean, we have some ideas for that, but to me, that's still something I couldn't say with certainty what is the origin. And we've seen this more recently in Iceland. Very similar periodic behavior. Really, really fascinating. It's linked to the dynamics of the flow of magma and the way gas escapes out of it.
I guess the last question I'll ask is just, thinking about the future of volcanology and the study of volcanoes, is there something that comes to mind that really excites you? Is there something about the future of this field that is really exciting that you look forward to?
If we think about these big historical eruptions, there are some real mysteries out there. I mentioned the 6th century. So in 536, we know from ice cores, and even we know from some Byzantine historical accounts, a dimming of the sun, that there was a colossal eruption somewhere on Earth, and another one in 540 or thereabouts. And then in 542, plague breaks out in Constantinople, the Mediterranean. This is the huge plague pandemic. It'd be great to figure out which volcanoes those were. And we have only the vaguest clues, really, that one is probably in the northern hemisphere somewhere. One is maybe tropics. So I think some of those, I would love to crack some of those mystery eruptions. We've got one in 1809, just over 200 years ago, an eruption the size of Krakatoa in 1883, somewhere on Earth, probably again tropical, because there's dust in both Antarctica and Greenland, so probably the volcano is in around the equator somewhere. 1809, it's not that long ago. No one has ever found someone who said, I was sailing a ship and there was this huge eruption. I'd love to track that down.
So mystery volcanoes, that's kind of an interesting thought and an exciting thing to think about.
I love the way that Clive talked about just, the soup is cooling down. So, all of that, like volcanoes and hot springs, that is the heat leaving the earth, right?
Yeah, in a way, it is, the second law of thermodynamics, entropy and process. But, I never really thought of it this way. There is something to be said for this period of time we're living in. You look at other planets like Mars, volcanism and, geological processes in that way are pretty much dead on Mars for the most part.
Why is that? Just because they're older?
Yeah, so Mars is a little bit smaller than Earth.
Okay.
So, it had less of that primordial heat. It had less of that radioactive decay heat. It just didn't stick around as long. We're kind of in this, and I'm just now really thinking about this. We're kind of this Goldilocks zone in the history of our
solar
planet's
system.
Geological history, that it's cool enough that the surface isn't molten or volcanoes everywhere, but we still have those kind of processes that are exciting, at least to me. Things like hot springs and fumaroles. And
should we be worried about the Earth cooling down eventually?
I don't think in the scale of humanity, that's probably not our biggest concern.
It's a billion years out.
We'll be hit with a lot bigger problems before we have to worry about
the global the heating of the Earth is currently the problem, not the cooling of it.
At least
in a billion years, maybe that's the alternative. But I found that interesting. Right, the Earth is cooling, even though the interior of the Earth is cooling while we are heating up the atmosphere and making it a lot harder to live here. But one thing that I also love to think about is every conversation we have, if it's not about space, a lot of our episodes are about space, but the ones that aren't, it always leads back to space in some way, right? And I kind of love that. And Clive was talking about, we're using these satellites, and those satellites are seeing the change in the height of the ground to determine if volcanoes are happening.
Yeah, it just comes back time and time again that, our eyes from space, whether it's, in this case, radar, or, hyperspectral imaging, looking at infrared.
What is hyperspectral imaging?
Just means looking at different colors of light. You can image ultraviolet, you can image near infrared, far infrared, all these different wavelengths, all these different colors of light you can look at from space. All of these tools give us, these, they really are the most powerful tools we have in some ways to look at problems that are on or questions that are on a real truly planetary scale. You can go as a scientist in the field with an instrument to a site and collect data, and you can fly things from aircraft and get kind of a regional sense for things. But if you really want to understand kind of these planetary scale changes, satellites are incredibly cool tools to do that. So think of obviously like Earth imaging, the Landsat missions, radar, hyperspectral imaging. If you have a problem, generally there's a way to kind of measure it from space.
It's kind of just, if you zoom out far enough, you're gonna see something.
Yeah, and you can see so many different places from, just a really couple hundred miles above us.
That's so cool. I do think it's just so fun again that I never thought we'd be going up into space to talk about volcanoes, but it is really every topic we hit, there's some sort of space related thing, which just makes you think about, how important space exploration and all that.
Yeah. I mean, it's that old answer to, why do we explore space when we have problems here on Earth? And that's because not only does it, satiate the curiosity and we do exploration and in the process create tools that, help us back on Earth, but it gives us these eyes that otherwise we probably wouldn't have if we just kind of stayed confined to the boundaries of our atmosphere.
Yeah. Yeah. It's a really cool thing to think about. And another interesting thing that we talked about, and we mentioned it several times in the episode, but we don't really get into detail about it. And I wanted to get into a little bit more detail here, is Tambora and the year without a summer.
Yeah.
Tell me a little bit more about that.
Yeah. So, I mean, the context, so Tambora is in, present day Indonesia.
Okay.
And
I didn't know that, but
and in 1815, so in modern terms, modern history, human history, there was this massive eruption. There was a series of eruptions, but one really big one from Mount Tambora in Indonesia, and that happened in 1815, and it ejected literally tens of cubic miles worth of material into the atmosphere, and of course, when you do that, that causes planetary scale, on that scale, planetary scale effects. And so Tambora injected...
We didn't have satellites up in the 1800s to check this.
But humans were around.
And we can see that now, modern day, even though we weren't recording this stuff, right?
Yeah, well, I mean, in 1815, we had to go to records. And so we have, the records of kind of what the effects on humanity were of the Tambora eruption in 1815. But you can also see the effects in, ice cores and tree rings and everything like that. But
all those scientific fields coming together once again.
Yeah. But if you think about, what happened, it really was, what we call, it would be the equivalent of what we call from nuclear war, nuclear winter, where you inject, large amounts of particles into the upper atmosphere, and it essentially blocks sunlight, and that creates global cooling. If you eject enough stuff into the atmosphere, instead of being a greenhouse gas and trapping heat, it just reflects the radiation back into space. And, I think scientists today have done calculations and think something like maybe a degree Celsius decrease in the global average temperature from Tambora, especially pronounced in the northern hemisphere, in Europe and even North America, where you had, what came to be called in 1816 the year without summer.
Mm-hmm.
And
the summer was just cold and they didn't really have one.
And there were failures of crop yields and
a major. I mean, and that leads back to what Clive was saying, which is one of the biggest impacts of volcanoes is that food insecurity that it causes, right?
It can be, yeah. And that scale of an impact, food insecurity is really one of the big problems. Because again, if you block out that solar radiation, that can impact crop yields, which have secondary effects. And that's not something that humanity is super resilient to, is impacts on food supplies. You've seen this. I mean, as the climate changes, as war happens, food insecurities can lead to massive migrations of people. And unfortunately, in 1815, we don't know exactly the causes of that. There were multiple eruptions and impacts on solar irradiance from the sun, but we think that eruption in Tambora in 1815 was one of the big causal factors to, in 1816, this year without summer. And, not only did you have failures of crop yields, but you had these shifts in climate patterns. So, in some places it didn't rain, and some places it rained way too much at a time of year they weren't used to. And that led to things like cholera outbreaks, we think. So there's all these kind of at least hints in the data that, these large scale eruptions can be real, impactful events in the history of our species, of humanity. It's definitely worth keeping an eye on.
Yeah, and it also just goes to show you how delicate the environment is and how one major eruption or decades of, ejecting carbon into the atmosphere can cause a lot of harm. And that's a volcano erupting and to that extent shows that kind of in a sped up.
Yeah, I mean, a lot of these planetary scale changes, and especially when it comes to climate change, we really think about derivatives, rates of change. It's not necessarily how much the atmosphere warms or cools, it's how fast that happens, and are we able to adapt to that? And in case of volcanoes, I think it's really a good indicator of what the impacts can be, because it's not always one thing. In some parts of the globe, it might cool down. Some parts of the world, it might heat up. You might get floods in one places and droughts in another. And that is really the story of our planet. It's a complex system, but single events or a few series of events can have real global scale impacts, and it's crazy to think about.
Yeah. So how nervous are you about volcanoes erupting? Is that a fear you have?
I don't think so. It's not something that keeps me up at night. I think there's probably bigger things that keep me up at night, but it's definitely something to keep an eye on.
Yeah, and like we mentioned at the beginning of the show, like we are in a very geothermically active area of the United States.
Oh yeah. I mean, that's what's so exciting to me about this part of the country that I've called my home on the West Coast, is we are in one of the more seismically and volcanically and just kind of geologically active regions of the world in general, certainly of the United States. And that has informed some of my own work, whether it's, these volcano in place, volcanic rock in place uranium deposits, whether it's, doing microbiology on the extremophiles living in, hydrothermal systems that are kind of fueled by hot rock beneath our feet. But it's exciting, and it's also a reminder of the power of the earth. It's it shouldn't be discounted how powerful these forces can be when they're unleashed into the domain of humanity.
Yes, I'm not one to play with them. Although you have. We've gone up and gotten stuck on a few mountaintops where you're like poking at a hot rock somewhere, and I'm like, Taylor, it's raining. We need to get down. So the last thing that I wanted to bring up was something that struck me that Clive talked about, which is kind of the interplay between science and policy, right? We know a lot about these things now, but like, are we getting this information to the people that need it in a culturally significant and sensitive way, in a way that's like most beneficial to them? And a lot of times it seems like these volcanoes that are erupting are in places where people maybe don't have access to the internet or all of the information. And I just think that that's such an interesting thing to talk about, even on a broader scale, right?
Yeah.
It's like that policy interaction.
Yeah, and I think what Clive was talking about is kind of a perfect little microcosm of what science faces, more generally, more broadly. And that is, you can't separate the science from the policy.
From the people.
From the people.
Yeah.
So I think that's one of our shortcomings as a scientific community, is we're very content generally as scientists to do our work and publish in journals and communicate to other scientists about what we're doing and teach and all these things. But when you divorce science from policy and divorce science from the people that it's impacting, you lose, I think, the most important thing, which is the reason we do science. The reason we do science is to increase, knowledge about the world that we live in, and try to make sure that that knowledge is used in a beneficial way to society to cure disease and stave off environmental degradation and devastation. And I think scientists sometimes aren't great at that. It's Clive is a great example of someone who has done incredible work at the intersection of science and the humanities, the science of volcanology, and also the kind of cultural context in which volcanoes exist. And that's both the historical context, but also the contemporary context of the, civilizations and the peoples that live around these incredibly powerful natural forces. And, Clive made a good point, which, on one hand, it's important to be able to communicate to these communities effectively the risks and the where the danger is and where the danger isn't. But it also is important to the science. It comes full circle, because there are oral histories and traditions that can tell us about maybe some of these mystery eruptions that we're still trying to understand. There are, civilizations that, their ancestors, their descendants are still here with those oral histories. And it's exciting to think that, there's that, you should go out and into these communities and communicate the science you're doing in an effective way. And in doing so, if you do that effectively, that can inform the science. And it's just another example, and it's something that's come up in this podcast several times so far, of that important interplay between science and the humanities. And so many times we try to silo them and say, you're a STEM major, you're a humanities major, well, I'm a scientist, you're a journalist. But it really is the context in which you do your work that's important. And it's important for folks in the humanities and studying cultures to understand science and history. of scientific events, but also, for scientists to understand that kind of cultural context in which they do their work.
It's something that I really, push a lot when we talk about the podcast. It's just, that interplay. I feel like we should hug or something now.
Yeah.
Or something, or shake hands.
That connection.
The STEM and the liberal arts come together.
But it is really important, right? And, we're not going to solve these huge, planetary scale problems that we face with science alone, no matter how well we study something.
Journalism is the only way to solve climate change.
Oh gosh, I don't know. But we develop all of this knowledge, and you can do the best science in the world, and if you don't find an effective way to communicate it and place it into the context of which you know it or discover it, I've said this many times before, you might as well not be doing science at all if you don't, make that translational piece to the people that it impacts. So yeah, it's fascinating. Clive has done some incredible work around science communication. I highly recommend everyone go see Into the Inferno. Clive has several documentaries now that he's done, and they're all beautiful works of art.
Look, my favorite way to experience volcanoes is on the big screen, and that's a nice way to do it. Not too hot.
I've drug you around to some volcanoes. Like I said, we live in a very interesting part of the country.
Maybe one day we'll get up to one and shoot an episode up there or something. Yeah. I'll be standing much further back, and you can be one of those like spaceman tinfoil suits.
Oh, okay, sounds good.
All right, Taylor. Well, it was great having Clive on. It was great to have this discussion. And, volcanoes, not something to be trifled with, but they're pretty cool and interesting.
Something to respect, and also something I think to, satiate that curiosity about some of these crazy things happening in our natural world and where we come from and where we might be going. So our thanks to Clive Oppenheimer, our guest this week. He is a professor of volcanology at the University of Cambridge in the United Kingdom. He has an excellent new book called Mountains of Fire, which I highly recommend you check out if you're interested in the stuff we've been talking about. And I hope you'll join us next time for Giant Leap.
Thanks so much.
It's one small step for man, one giant leap for mankind.
And then we go. Hang on.
What is that? I think you should do that.